The way we think about artificial intelligence has been fundamentally reshaped, not by bigger models, but by a quiet revolution in how they're trained. We've spent years chasing scale, more parameters, more data, more compute. But the real breakthrough isn't in size, it's in strategy. And the strategy that's quietly rewriting the rules is direct preference optimization. Let's go back. For years, training large language models meant predicting the next word, a massive autoregressive task. We de-feed them trillions of tokens, and they'd learn patterns through statistical inference. But this approach had a flaw. It didn't teach models what we actually want. It taught them what's common, not what's correct, helpful, or truthful. Enter reinforcement learning from human feedback, or RLHF. This was the first major shift. Instead of just predicting text, models were trained to align with human preferences. Humans would rate responses, which answer is better, and the model would learn to favor responses that scored higher. It worked. Models became more helpful, more polite, more aligned. But RLHF had its own problems. It was expensive. It required thousands of human raters. It was slow. And most critically, it was fragile. Small changes in reward modeling or training dynamics could send models spiraling into undesirable behaviors. The process was like tuning a high-performance engine with a wrench and a guess. So researchers began asking, can we skip the reward model entirely? Can we train models directly on human preferences, without the middleman? That's where direct preference optimization, or DPO, comes in. And what's remarkable is that DPO isn't just a tweak. It's a paradigm shift. Let's break it down. In traditional RLHF, the training pipeline looks like this. First, you train a reward model to estimate how good a response is. Then, you use that reward model to train the policy via reinforcement learning, typically using PPO, proximal policy optimization. It's a two-stage process, and it's computationally heavy. DPO flips this. It doesn't need a separate reward model. It takes the pairwise preference data, the A is better than B judgments, and uses them directly to update the model's policy. How? Through a simple but powerful mathematical transformation. DPO reformulates the reinforcement learning objective into a supervised learning problem. It does this by expressing the policy update as a function of the likelihood ratio between the chosen and rejected responses, and then minimizing a cross-entropy loss. Let's get technical for a second. In standard RLHF, the policy update involves maximizing the expected reward. J theta equals E. But with DPO, we eliminate the reward model and instead optimize. L DPO theta equals E. Where is the current policy? Pi ref is the reference policy, usually the previous model. Sigma is the sigmoid function. Beta is a temperature parameter. And the expectation is over preference pairs. The key insight? This loss function directly encodes the preference data. The A is better than B, without needing to estimate a reward score. It's like going from a noisy indirect measurement to a direct calibrated signal. And the result? You can train a model on preference data using standard supervised learning tools. No reinforcement learning, no PPO, no complex reward shaping. Just a simple cross-entropy loss. But here's where it gets even more interesting. DPO doesn't just simplify training, it improves stability. Because you're not optimizing a reward model that can be biased or misaligned, you're directly aligning the policy to human preferences. No intermediate layers of approximation. And the performance? In practice, DPO matches or exceeds RLHF in alignment quality, but with dramatically lower compute. Studies show DPO can achieve comparable results using 30–50% less training compute, and often with fewer training steps. Even more striking, DPO doesn't require a separate reward model, so you can train on the same data you'd use for RLHF, but with a much simpler pipeline. You can train a model in days, not weeks. You can fine-tune on smaller datasets. You can run experiments faster, iterate more, and scale more efficiently. But DPO isn't perfect. It assumes the reference policy is close to the optimal one. If the reference model is poor, DPO can degrade. It's also sensitive to the temperature parameter beta, too high, and it overfits to the data, too low, and it underfits. So researchers have built on DPO, introducing DPO with adaptive beta, DPO with KL control, and even DPO with multiple reference policies. These variants refine the original idea, making it more robust and scalable. And now the real kicker, DPO isn't just a tool for language models. It's a framework. It's being applied to vision models, robotics, multimodal systems, anywhere you have preference data. In fact, some of the most advanced models today, including those powering cutting-edge AI assistants, are fine-tuned using DPO or its derivatives. It's not just a research curiosity. It's the new standard. So what does this mean for the future of AI alignment? It means we're moving from complex, fragile systems built on multiple layers of inference to simpler, more transparent, and more efficient methods. We're replacing reward models with direct supervision on human preferences. We're reducing the black box in alignment training. And we're making it possible for more researchers, even those without massive compute budgets, to contribute to building safer, more helpful AI. The shift from RLHF to DPO isn't just about efficiency. It's about philosophy. It's about recognizing that human preferences are the ultimate goal, not reward scores, not token probabilities, not model confidence. And now, we have a way to optimize directly for what matters. So the next time you interact with an AI that gives thoughtful, nuanced answers, that avoids harmful content, stays on topic, and understands your intent, remember, behind that behavior is a quiet but powerful idea. One that doesn't rely on guesswork or indirect signals. One that says, let's just teach the model what we want directly. That's the power of direct preference optimization. Not just a faster training method, a smarter way to align AI with human values.